Okay, good evening, everybody. This is Professor Ayorinde welcoming you to your first online review session in organic chemistry for the spring 2014 semester. Oh, rather, I'm sorry, for the fall 2014 semester. Oh my God, I said spring. This is the fall 2014 semester. So what we are going to do today, we are going to review for exam number 3. And since most of you are in Dr. BAKARE's class, we are going to use his previous exam number 3 for today's session. And also, since this is your first time of using this system here, I do want to show you a few of the functionalities. Anytime you want to ask me a question, if you can see my cursor, you could click on this icon here, and then this is the mic, and then you could go ahead and ask your question. Of course, if you want to show your video, you could also click on this video icon here, and then you could show your video. In addition to that, if you want to send me a question through the chat window, this is right here. This is your chat window right here, if you can follow my cursor. And also, if you want to ask me a question and you want to get my attention, if you look right here, follow my cursor right here, there is an electronic hand. Just click on that, and then I will know that you want to ask me a question, and I will call on you. Also, if you want to send me, if I ask you a question and sometime I ask you to give me a smiling face or applause or whatever, I just click on this icon here, and that gives you this series of emoticons, and then you could click on any one of them just to show your emotion. Okay, so at this point we are going to start the session. I noticed that many of you have joined us. I will recognize you as we go along during the course of this session. So what we want to do now, we are going to go straight to the first question that we want to do today. By the way, we are going to do questions 3, 5. We are going to do questions 3, 5, 6, 7, and if we have some time, we might do question 2, okay? But because we do want to get out of here around 8 o'clock today. Okay, so at this point, let me go to the first question that we want to work on, which is question number 3. Now, if you guys see question number 3 on your screen, can you give me a happy face? If you see question number 3 on your screen, give me a happy face. Okay, excellent, excellent, great, great. Okay, great. Okay, good. Okay, so at this point, let me call on Ayana. Can you do us a favor here and read question number 3 for us?
Predict the major organic products of the following reactions.
Okay, thank you very much. And also, when you do give the major organic products of these reactions, you also need to indicate the regiochemistry or stereochemistry. Okay, so the first question we have here, we have this compound here, compound A, and we are given this reagent here. Okay, so we have sulfuric acid in in water, supposed to react with this alcohol here. Does anybody know what kind of alcohol is this here? What type of alcohol is that? You could send me your response through the chat window. If you just say, if it is tertiary, say 3. If it is primary, say 2. Okay, great. Okay, great. Okay, very good. It is a tertiary alcohol. So therefore, you want to react a tertiary alcohol with sulfuric acid. So what would that give you? Sulfuric acid with a tertiary alcohol. What do you expect to happen here? Okay, what do you expect to happen here? Sulfuric acid in the presence of dilute acid. Anybody? Okay, great. Alkene formation. That is excellent. That is correct. In other words, anytime you have an alcohol and you have particularly secondary or tertiary alcohol and you have a dilute acid or even strong acid, what you expect to get is an alkene. In other words, you are going to get what we call dehydration. Okay, so this is a dehydration reaction. Okay, so let us go ahead and write the product here. Take this out of here. Okay, I do want to ask you another question before I write the product though. Let me go ahead and number this compound here. Okay, let us call this carbon 1 right here. This is 2. This is 3. This is carbon 4. Carbon 5. Okay, and say this is carbon 6. Okay, if we are going to form an alkene, do you expect the major product to be between? Oh no. Okay, let me ask you this way. Where do you expect the alkene product to be? The carbon-carbon double bond. Just give me the numbers. Is it between 1 and 2, between 1 and 5, or between 1 and 6? Between 1 and 5. Excellent. That is correct. Why between 1? Oh, yes, also between 1 and 2. That is correct also. Why between 1 and 5 or 1 and 2? Anybody has an idea? Tertiary is more, okay, because you get a more stable alkene product. Excellent. That is the correct answer. So let us go ahead and write the answer here. Since they told you to write the okay, so that would be your major product. That would be your major product. Okay, that would be your major product. And of course here will be your minor product right here. This is your minor product. Because in this here, you have a tetra substituted alkene. This is a tetra substituted alkene. And that will be more stable than this one here. The minor product will be a di-substituted alkene. And we all know that tetra-substituted alkene are more stable than the di-substituted alkene. So therefore, this is our major product. Okay, so let us go to the next question, B. Does everybody follow that? If you follow that, give me a happy face. Okay, very good, very good. Okay, so most of these reactions on question number 3, of course, these are mostly testing your knowledge of the reagents. In other words, do you know what the reagents do? Okay, that is very important. Okay, so let me clear this here. Yes, somebody has a question. Christiana, go ahead and ask your question.
Do they say tri-substituted instead of tetra-substituted? Because we have 3 alkyl groups.
Yeah, oh, thank you so much. Thank you. Yeah, is try. I wanted to say try. Good, that is excellent. Try substituted. Thank you so much. Okay, whereas this here is a die. The second one is die. Okay? Okay, thank you. Okay, so let us go to the next one. Okay, for B, what do we have for B? Once again, we have this reagent here, mercury acetate in water, followed by sodium borohydride. And now, does anybody know what that reagent will do to a carbon-carbon double bond? What does it do to a carbon-carbon double bond? Anybody has an idea? What does this reagent here, the combination of this reagent, what does it do to a carbon? Okay, hydroborase. No, you're almost there. Markovnikov addition of water. Excellent, excellent. That is correct. Markovnikov addition of water. Excellent. That is correct. Okay. You guys know your reagents. I could see that. Okay, so let us see here. So therefore, what we are saying here, this reagent will add water across a carbon-carbon double bond such that the hydrogen will go to, in this case, the hydrogen will go to the carbon that has more hydrogen, which is here, and the OH group or the hydroxy group will go to the carbon that has less hydrogen, which is this one here. So therefore, what is going to be the product? And we call that kind of reaction Markovnikov addition. We say that is a Markovnikov reaction. Okay, so let us see what is the product. The product will be this here. And take this out of here. Okay, so what do we have here? We have hydrogen, this hydrogen here, okay, is adding to this carbon here. And of course, this hydroxy group or OH group is adding to this carbon here. And so we call this a Markovnikov addition of water across the carbon-carbon double bond. And that is what this reagent will do. Folks, it is most important that you know what all these reagents do. So you need to make a catalog of reagents, and once you have a catalog of reagents, write in your own words what those reagents will do. If you can do that, you will find that you have no problem with organic chemistry. Okay, so let us go to question number C. Somebody has a question here. We will need to know the actual mechanism that the major products. No. In this particular question here, nobody is asking you for the reaction mechanism. Okay? If they do not ask you for reaction mechanism, you do not have to give it. Okay, so just in this particular instance, just give the product of the reaction. That is all. Okay, so let us do C. I think I see some questions here. Okay, yeah. Let us do C. Okay, let me take this out of here. Okay, so this here is for B, so let us take that out. Okay, for C, what we have a carbon-carbon double bond. And we have this reagent here. Once again, this is a question of knowing what your reagent will do. Okay, so I do have a question for you guys. What does potassium permanganate followed by dilute acid, what does it do to a carbon-carbon double bond? Anybody has an idea? Cleavage. Exactly, cleavage. Okay, it cleaves okay, very good, excellent. Okay, it cleaves the double bond. Then what happens to the carbon of the carbon-carbon double bond? Anybody has an idea? Say, for example, if a carbon of the carbon-carbon double bond has an hydrogen attached to it, what happens to that carbon? What happens to that carbon if it has an hydrogen attached to it? For example, you look at this here. It cleaves, excellent. It cleaves to give a carboxyl group. Okay, that is what I want to hear. Okay, very good. So therefore, let us look at the product for this. Take this out of here. Okay, so the product will be, what we want to do now, we want to cleave this right here, right? Okay, so we are going to cleave it. So we have this here. I'm going to write it big enough so that you guys can see what is going on here. So it cleaves this here. This carbon here that does not have an hydrogen becomes the carbonyl of a ketone. And this carbon here that has an hydrogen attached to it becomes the carbonyl of a carboxyl group. Okay, so therefore you have this. Okay, so that will be the product of this reaction. You notice here, the rest of the molecule is still here. The rest of the molecule is still here. Nothing happens to it. Okay, so all that we are focusing on at this point is the fact that this reagent will cleave a carbon-carbon double bond. The rest of the molecule is there. No matter how big the rest of the molecule is, it has nothing to do with that reaction. For example, if I give you this here, supposing I give you this here, I do this, okay? So what is the product of this? Okay, of course, you guys already know that we are going to cleave this. Okay, this carbon becomes carbonyl of carboxyl group. This carbon becomes carbonyl of another carboxyl group. So therefore, we get this product. And you notice here also, this part of the molecule has nothing to do with it, and it's still right here. Okay, so that is the point I want to make here. The focus is on the carbon-carbon double bond, okay? Okay, so let us now come back to here. Take this out of here. Okay, so this is the product of this reaction right here for C. Okay, now let us go to D. Let us go to D. Okay, to do that, I am going to take this out. Okay, just for clarity, take all this out. Okay, in D, again, we are going to react another molecule, another reagent with a carbon-carbon double bond. In this case, it is bromine. in methylene chloride or dichloromethane. This here is just the solvent. This here is just the solvent. All the solvent does is just to allow the reagents or the molecules to mix together. That's nothing to do with the reaction. The actual reaction is taking place between bromine and this carbon-carbon double bond. Okay? Okay, so let us see. Let me ask you a question here before we move on. Take this out of here. What happens with bromine and a carbon-carbon double bond? What kind of product do you get? Or do you expect to get? Yes. Addition of halogen. Okay, great. Somebody asked a question for me. Alright, go ahead and ask your question. Or you could send me this question through the chat window. Okay. Okay, no question. Okay. Okay, so you say addition of anti-addition. Excellent. Excellent. Okay, Chelsea say anti-addition. Okay, very good. Okay. Already I saw your question. I will come back to your question. Okay. Very good. Anti-addition of two bromine atoms across the carbon-carbon double bond, and that is what you expect to get here. You have anti-addition. So therefore, what does that mean? Let us write the product. So you have this here. Okay, you have the ethyl group, and then you have one bromine here, and then the other bromine will be here, and of course hydrogen here. So what you have here, we have two bromine atoms. We have two bromine atoms, this here and this here, added across the carbon-carbon double bond, such that those two bromine atoms are anti to each other. In other words, they are on opposite sides of the ring system. You can see here, this bromine is going away from you, this here, going away from you. On the other end, this bromine here is coming at you. Okay? Okay, so is there any question on this? Yes, alright, go ahead and ask your question again. Oh, okay. I see you sent me a question. You said, is the solvent non-nucleophilic? Let us see the solvent that you are looking at here. Yes, this solvent here, the dichloromethane, which is this solvent here, it is non-nucleophilic. Okay, if that is the question you are asking. It is non-nucleophilic. In other words, it cannot react as a nucleophile. Yes? Okay, yes. Okay, good. Aure also says, supposing the solvent is methanol. In other words, Aure is saying, supposing the solvent is this here. Let me take this out. Aure is asking us, instead of dichloromethane, supposing the solvent is methanol. Okay. If that is the case, you are going to get an ether. So I don't think we want to go into that right now, but I will come back later to that. But if that is the case, instead of getting the dibromo compound here, what you might get is this also. What you get, one of these will be, because the methanol here, because this methanol will be acting as a nucleophile because of this non-bonding pair of electrons and oxygen. So therefore, in that case, what you are going to get will be this right here. Okay? That is in the case if this solvent here, if it is a methanol, and also if this solvent is water. If this solvent is water, then you also expect to get something different. In that case, instead of this, you get what we call a bromohydrin. Okay? So the product you get here depends on what the solvent is. But the point is, I don't want you to miss this point. Anytime you see this reagent here, bromine in dichloromethane, right here, what you get is dibromide, in which the bromine atoms are anti to each other. Keep that in mind. And sometimes, instead of the dichloromethane, you may also use DMSO. That is also a non-nucleophilic solvent. This here is also a non-nucleophilic solvent. So if you use any non-nucleophilic solvent in the presence of bromine, you will get the addition of bromine atoms across the carbon-carbon double bond, such that the two bromine atoms will be anti to each other. So let us come back to our original question here. So in this case, of course, it will be this here. Okay, very good. That was a good question, by the way. Okay, the stereochemistry of somebody also is asking, this is Dominic asking a question, is the stereochemistry always the same? Yes, the stereochemistry is always the same, no matter which one or which solvent you use. Always trans or anti-addition. Very good. Okay, so let us go to take this out of here. Take this out of here. We all know this now. Take all of this out of here. So now let us go to question E. Question E. Okay. Question E. Okay, question E, what we have here, we also have a carbon-carbon double bond. And we have this reagent here. Okay, can anybody tell me what does this reagent do to a carbon-carbon double bond? Okay, formation of cyclopropane. Yes. Yes, correct. Excellent. Tesla said cyclopropane. Chelsea says cyclopropane. All of you are correct. Okay, so anytime you see this reagent here, folks, I keep coming back to this, know your reagent, know what they do. Okay, anytime you see this reagent here, what it does is to add a carbon atom across a carbon-carbon double bond, such that those two, that carbon atom will be attached to two hydrogen atoms. Okay, for example, in this case, the product is going to be here. We have this here. Notice that the rest of the molecule has nothing to do with this reaction. So you have this. Okay, so what we have here, we have the cyclopropane ring is formed. Okay, so that's a cyclopropane ring system that is formed, and that is what this reagent will do. This reagent here, anytime you have, we call this a diiodomethane, diiodomethane. Anytime you have diiodomethane, and of course in the presence of zinc, copper amalgam, which is a mixture of zinc and copper, and then you have a carbon-carbon double bond, what you have is the addition of carbon to the carbon-carbon double bond to form what we call a cyclopropane ring, which is this here. As you can see here, this carbon here, you have two hydrogen atoms attached to it. Okay, so that is what that does. Okay, now let us do F. No question on that. F. Let me take this out of here. Okay, now we want to do F. Okay, here again we have what we have here. So all of these are reactions of alkenes. We have a carbon-carbon double bond. And then we have this reagent here called MBS, N-bromosuccinimide. Anytime you have N-bromosuccinimide, MBS, think of it as bromine. Okay, think of it as bromine. Okay, of course, what we have here, we have water, which is a nucleophilic solvent. And then, of course, DMSO is also another solvent just to mix everything together. Okay, now, so this question is related to the question that I already asked me earlier. We have bromine, like I said, anytime you see MBS, think of it as bromine, okay? So you have bromine in water and double bond, okay? Then what do you expect to get? What happened to this? What does bromine and water, what does it give you with a carbon-carbon double bond? Bromine and OH, excellent. Yes, perfect, perfect. Anti-addition, okay, exactly. Anti-addition of bromine and OH across the carbon-carbon double bond. Okay, so you guys know your reagent. Very good. Okay, so let us, okay, so the point here is anytime you see MBS, in this particular instance, and then you see water, then you know that think of the MBS as a source of bromine, which is this bromine here, okay? Okay, so let us take it out of here and then give you the product. So the product will be, since you guys have already told us, okay, so we have the methyl group right here, and we have bromine here, and then of course the OH will be here going away, and hydrogen is here. So what we have here, we are adding, in this particular reaction, we are adding bromine and hydroxide across the carbon-carbon double bond such that both the bromine and the hydroxide are anti to each other. In other words, they are trans to each other. Okay? Very good. Okay, now if you follow that, give me a happy face. If you follow that, give me a happy face. Okay, good. Okay, alright, go ahead and ask your question. Oh, okay, so, okay, I got you. Very good. Okay, now let us go to G, question G. Okay, let me take this out of here. G, okay. Now, another case of knowing your reagents. Okay, you have this molecule here, we will call this, sometimes we abbreviate as M-chlorobenzoic acid. So if you just see MCPBA, that is this molecule here. Okay. Okay, Ayana, I'll be right with, yeah, okay. Tamara, go ahead and ask your question. Oh, okay, let's see. I thought OH would be on mouse. Where is the, let's see. Oh, no, okay. Okay. How do you know CH3 is pointing towards you for C? Okay, let me go back to that. How do we know that CH3 is that C? Oh, okay. Let me come back. Let me finish this question here, then I'll come back to this one here. If somebody's asking a question. They thought that this would be mechanical reaction, but not so. Okay, let us look at this. M-chlorobenzoic acid, what does it do? What does it do to a carbon-carbon double bond? What does it do? What does it do to a carbon epoxide? Excellent. Okay, so it's a question of knowing your reagent. So in this case, the product will be this here. And so this is our epoxide. Okay, so that is what this reagent will do, the M-chlorobenzoic acid. Okay, now, once you then add dilute acid to the epoxide, what do you expect to get here at this point? Okay, you now form your epoxide. At this point, you have dilute acid. What do you expect to get right here with this reagent? Sorry, this reagent here. Okay, what would that give you? Reacting with the epoxide. What would that give you? Okay, break up the epoxide and have OH. Excellent, excellent, great. It will give you a diol. You know that was what we call a diol. Okay, in other words, you have two OH groups at you have two OH groups added to the carbon-carbon double bond, okay, to form what we call a diol. So let us see what the product will be. Take this out of here. Okay, so this reagent here, what does it do? It gives you this product. Okay, so now you have OH here, and then another OH here. Notice they are trans to each other, anti to each other. Okay, okay, you have a question or just no question? Okay, so what does this reagent do? When you have this, sometimes instead of having this written as sulfuric acid and water, you may have it written just as this, as hydronium ion. Okay? It might be written as hydronium ion. Okay, so therefore, this one will give you a trans addition product. This is trans addition. Okay, so therefore, anytime you have an epoxide, you have hydronium ion. I'll write this here, hydronium ion or sulfuric acid in water. What you get, the epoxide will open up, this epoxide will open, and then you're going to get the trans diol. In other words, the two OH groups will be opposite side of the ring system, anti to each other. And so therefore, supposing I give you this here, supposing I do this, let's just take a look at it. Supposing I do this. Okay. So step 1, M-chlorobenzoic acid, and then I say step 2, hydronium ion. What product do you expect to get? What product do you expect to get? Anybody? What happens? What would this reagent do? OH or Oh, okay. You guys are communicating with each other. I see that. Okay, supposing I give you this here, what product do you expect to get? Okay. Nope. No. Keep in mind, I say step 1, then step 2. No, this is the reagent I'm giving you here now. Okay, so what do you expect to get? Exactly, 1,2-diol. Exactly. Because this will go straight to 1,2-diol. Since I say step 1, step 2. Therefore, this will be this one here. Okay. And of course, this is here. And this is here. Oh, yeah, okay. This is here, okay? So you are going to get, in this case, you are going to get, okay, this here, okay, the OH here and this OH here, they are on opposite side of the ring system, what we call anti-addition, okay, which means that they are trans to each other, or sometimes we can use the word trans, okay? Okay, let us go back to the question. Not that one. Okay. Now let's go back to here. Take this out of here. Yeah, go ahead, ask your question. Oh, it makes, oh, okay. I got you. Now, after I've done that, I promise you guys somebody wanted some clarification on question F1. Let us go back to that. Okay. Okay. I gave this product for F1, which is this here. I said this will be the product. Okay, I said also that you will get this here, bromine will be here, and the other, the water will be here, trans to each other, and of course hydrogen is here somewhere. Okay, somebody asked that how come the OH is not here? Somebody say, how come the OH is not here and the bromine not here? Okay, actually in this particular reaction here, you are going to get both of them. You are going to get a mixture of isomers. Okay, so that will be the answer to your question. I know that I only gave this here. You will also get another product in which, just a minute, I'll be right with you. You get another product in which the OH will be here and the bromine will be here. So you are going to get two products, okay? Okay, now, so let us now go to, okay, for F, why isn't it, no. This is not a mechanical, you do not have mechanical reaction here. Mechanical reaction is whenever you are adding hydrogen and a nucleophile across a carbon-carbon double bond. So that is not the case here. Okay, Ayana, go ahead and ask your question. Okay, can CH3 be placed behind? Yes. Yes, it could go both ways. Hello? Yeah, Ayana is asking, can we place? Yeah, go ahead.
How do you get the Br to be on the same carbon as the methyl? Wouldn't it be, because wouldn't a carbocation form in that mechanism?
Oh, no.
Wouldn't you want it to be a tertiary one?
No, you are not forming a carbocation. You are forming an bromonium ion. Remember, I told you that the MbS is a source of bromine. So you are forming a bromonium ion. And when you form the bromonium ion, okay, say you form a bromonium ion, okay, what happens? The incoming nucleophile, either in this case, it will be the water acting as a nucleophile, could come from both sides, okay, could come from come on this carbon here, or come on this carbon here, okay. So therefore, yeah, so the water could come attack this carbon, or could attack this carbon, and that is why you end up getting a mixture. Is that clear, Ayana?
But wouldn't it want to attack the more substituted carbon?
Oh no, okay. I see what you're saying. Now, what is going to happen here? If you have this, okay. Let me go back to. Let's go to a new page. Supposing you have this. Okay? Okay, so now you have the bromonium ion is here. Okay, here the metal is here, and here the hydrogen is here. So water is coming in. The water comes in. Now what I'm saying here is, yeah, but I do get your point. What happens here, this water comes in, attack this carbon here, thereby opening this up. Okay? It could also, at the same time, come here, attack this carbon here, and this also opens up. Now, the question that you have in your mind is, which will be the major product? Will it be the attack on this carbon here, or the attack, let us call this carbon here, say carbon A, and this carbon B. Now, which will give you the major product? Will it be the attack on carbon A, or will it be the attack on carbon B? I will probably tell you that the attack on carbon A will be the major product, because carbon A is less in that. But that does not mean that you are not going to get attack on carbon B. Okay, so that is why you end up getting a mixture of products. Okay, so let us move on this. Okay, come back to here. Okay, now let us come back to here. Now let us do H, because our time is moving fast. Okay, let us do H. Okay, question H. Take all of this out of here. Okay, go ahead. Christiana, go ahead and ask your question.
So are you trying to say that the major product is found at A, or is found at B, or they have like equal amounts?
Oh no. The major product will come from the attack on A. If I say major, you know that it cannot be equal amount. Okay? The attack on B will be the minor product. You follow that?
Yeah.
Okay. Okay, so the major product will come from the attack on A. Okay. Okay, so let us do H. Okay, I know this one is a fairly simple one. Okay, what we have here, we have a carbon-carbon double bond again, and here we have osmium tetroxide in the presence of N-methyl morpholine N-oxide. You don't need to have know that long name. All you need to know is that you have NMO. Okay, so anytime you have osmium tetroxide in the presence of NMO reacting with a carbon-carbon double bond, what kind of product do you expect? What does this reagent, what does it do? Okay, syn addition of, oh, yeah, exactly. Okay, you form a diol, syn addition of two OH groups. Excellent. That is what that gives you. Okay, so let us say what the product is going to be here. Take this out of here. So the product will be this. Okay, so we say syn addition. Okay, therefore, what this reagent will do for you is to add two OH groups across a carbon-carbon double bond such that those two OH groups will be on the same side of the ring, or they will be what we call cis to each other, or sometimes we say syn. Okay, so this will be a syn addition of two OH groups across the carbon-carbon double bond. Now, sometimes instead of using NMO, supposing I have this, supposing I have that, I will also do this. Osmium tetroxide followed by sodium, hydrogen, sulfide. That would do the same thing as what we just did. In other words, to get addition, syn addition of two OH groups across the carbon-carbon double bond. Okay? Okay? So therefore, this reagent also, if you have this combination of reagent, it will also add OH and OH to a carbon-carbon double bond in a syn or cis addition fashion. Okay? Okay, so let us go back to question 3 again. Okay, we are almost through with question 3. I spent some time on this because this gives you an opportunity to review your reagents. So those knowing what those reagents do is most important in organic chemistry. Okay, now let us do I. Okay, you have this combination of reagents here. Okay, you have borane followed by hydrogen peroxide in hydroxide. What does that do to a carbon-carbon double bond? What does this reagent do to a carbon-carbon double bond? Oh, Christiana, what is your question, by the way?
I'm sorry, no question.
Oh, no question, okay. Okay, Kessler said it has this reagent here. This is boration. Okay, anti-Markovnikov addition of water. Excellent, excellent. In other words, you are going to add water across the carbon-carbon double bond. Okay, so this is just a case of knowing your reagent. So therefore, anytime you have this reagent here, what does it do? It will add water across the carbon-carbon double bond in such a way that the hydrogen goes to the carbon, this carbon here that has less hydrogen, and the OH goes to this carbon here that has more hydrogen. In other words, this is an anti Markovnikov addition is an anti-Markovnikov addition of water. Okay, so what is the product here? Let's see what the product will be. So we have this here, this here, this here, and then we have this here. So we say the OH will go here, so OH goes here, and the hydrogen will go right here. Okay, in this case, also let me show the stereochemistry here, even though we realize the stereochemistry is not important here, but I just want to make that point. Now this reagent, what it does, it adds hydrogen and hydroxide across the carbon-carbon double bond in a syn addition fashion. So this is a syn addition reagent. In other words, it will add the hydrogen and hydroxide across the carbon-carbon double bond such that those two hydrogen and hydroxide will be on the same side of the molecule, or they will be syn or cis to each other. Okay. Now we therefore say this here. We say this reaction is stereospecific. Okay. It is also regiospecific. Regiospecific because it adds the hydrogen and hydroxide in a particular fashion. In this case, in an anti-Markovnikov fashion. Okay, so that is why we say this reaction is both stereospecific because you only get one stereoisomer, and we also say it is regiospecific because the hydrogen and hydroxide go to a particular part of the carbon-carbon double bond. Okay, syn addition of the, okay, good. Okay, very good. So the net process here is a syn addition of water across the carbon-carbon double bond. Okay, so let us go to the last one, J. Take this out of here. Okay, J, what do we have for J here? J, we have a carbon-carbon double bond reacting with hydrogen bromide. Okay, what do you think will happen here? What do you think will happen? Hydrogen bromide adding to a carbon-carbon double bond. What will happen? Markovnikov product, okay, great. Markovnikov addition of hydrogen and bromine across the carbon-carbon double bond. Excellent. You guys know your reagent. That is what you need to do. You need to know your reagent. Okay, so therefore the product will be this. Say Markovnikov addition, the hydrogen will come here, and of course, so that means you are going to get CH3. Okay. Just to show that the hydrogen is here. We have this hydrogen, and then on this carbon here, you have the, okay. Now this reaction, we say this reaction is regiospecific. We say this reaction is regiospecific, but it is not stereospecific, because you get a mixture of stereoisomers. Okay? Okay, now, once you form this product here, and then they now ask us to now use this reagent here. Okay, you have hydroxide in methanol as solvent. What is going to happen here? What is going to happen here? Anybody has an idea? What will happen here? Going from here reacting this here with this, what is going to happen? Debromination of X, excellent. We're going to form dehydrobromination. Dehydrobromination. In other words, you are going to lose hydrogen and bromine. So you are going to form an alkene. Let us move this a little here. So you are going to form dehydrobromination. Okay, so how are we going to do this? Let me label this, let me number this molecule here. Let us say this is carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. Can anybody tell me, okay, I also want to let you know here, there is hydrogen here. Okay. Okay, can anybody tell me where are we going to form the carbon-carbon double bond? Because you guys say we are going to lose hydrogen and bromine. Okay, between 2 and 3. Excellent, excellent, great. We are going to between 2. Why between 2 and 3? That is correct. Okay, Chelsea said between 2 and 3. Ayana said between 2 and 3. Those are correct. Excellent. Okay, why? I know you gave me the reason before. I just want to hear it again. Why? Tri-substituted, exactly. More stable than di-substituted alkene. Excellent. Okay, so therefore the product will be this here. Be this, double bond is here, and then this is here, I believe, yeah, this is here, and of course this is here. Okay, so let us see here. Let me see if we can, where do we start from? Okay, okay. Now, so we see now this will be the product here. For this will be the final, oh, sorry. So this will be the final product right here, okay, because we are forming the double bond between, we are losing this hydrogen here, and then we are losing this bromine here, so therefore we form the double bond right here, and that is what we have here. And of course this here, this group here, this is this methyl here, and of course we also have this methyl here, and that's what we have here. And of course we have methyl here, and that's what we also have here and here. So this is the product here. Okay, folks, we have finished question 3. We did spend a lot of time on this. What I want us to do now, let us go to question number 5, because I think it's a very important one. Question number 4, I want to skip question number 4 because it is similar to question number 3, just a question of knowing your reagents, and then so that is just pure memorization. So at this point, let us go to question number 5. Because it is past 8 o'clock, we spend about 15 more minutes and then we call it a day. Question number 5, let us see here. Christina, can you go ahead and read question number 5 for us?
Outline a reaction scheme to show how you will convert A to B below.
Okay, thank you very much. Okay, so what this is asking us to do is to outline a reaction scheme to show how you will convert compound A to compound B. Okay, now what this is, when you get to this kind of question here, you need to know your reagents. You need to know all of those reagents that we use in question number 3. Okay, that is what this is testing here. Because now we are now dealing with what we call a synthetic scheme or reaction scheme. Okay, synthetic scheme or reaction scheme. So when you have this kind of problem, what you need to do, take an analysis of the problem that you have. Take a very close look at the starting material. If you take a look at this starting material here, in this starting material we have that this starting material here are this carbon-carbon double bond, of course, attached to the ring system, which is here. Also, similarly, we have the carbon-carbon double bond still here. Now, what is the difference now? Now, what is the difference? You now have, in addition to this carbon-carbon double bond, we now have a methyl group. We now have a methyl group. In other words, what have we done? We have joined a methyl group to this carbon here. Okay? So therefore, whatever we do, we need to be able to do that. Then the first question that should come to your mind is, what reaction will allow you to form a new carbon-carbon bond? Can anybody tell me? What reaction will allow you to form a new carbon-carbon bond that you know of? What reaction? What reaction will allow you to form a new carbon-carbon bond? Acetylide reaction. Excellent. Acetylide reaction. Okay, very good. So once you know that, I think we are home free. You know, we are almost there. Okay, so let us now see what we can do. When you have this kind of problem, if you can, try to see if you can work backward. Okay, work back from the starting from the product, work your way back one step at a time until you can get yourself back to work backward until you can get yourself from the product to the starting material. Okay, so that is what we want to do now. Okay, let us go. The first thing I'm going to ask myself is, okay, I want to form a trans-alkene. Okay, I want to form a trans-alkene. I don't know whether you've done this already, but if you have not done this, I'm sure you will do this before your exam. So I know you'll still have a class on Friday. Now, to form a trans-alkene, there is only one reagent that you guys will know before your exam, and that is this reagent here. Okay, you will start from an alkyne. You start from an alkyne. Okay? You're starting from this alkyne here. For you to get a trans-alkene, this is the reagent you need to do that. Take this out of here. And that reagent is called that reagent is lithium in ammonia. If your professor has not given this reagent to you yet, he will give it to you before your exam. Or you could use either lithium in ammonia as solvent or sodium in ammonia. Anytime you use this reagent here with a carbon-carbon triple bond, what that does is to add two hydrogen atoms, one here and the other here. What it does is to add two hydrogen atoms across the carbon-carbon triple bond, such that you are going to form a trans-alkene. Okay, so that much you know at this moment. Okay, so we are going to do that. Okay, let's see here. Sorry about that. Okay, so now we form this. We form the product coming from this alkyne. Then the next question you want to ask yourself is, how do I form this here? How do I form this alkyne? That is the next question you're going to ask yourself. Okay? I will say, okay, I could form this by this reaction. If I take acetylide, in this case sodium acetylide, and I react with methyl bromide, this carbon of the acetylide will act as a nucleophile to attack this carbon of the methyl iodide, methyl bromide, and therefore you are going to form this product. Okay, I'm sure that is what you did today in class. Okay, this is acetylide reaction. Okay, and this will be what we call alkylation. So we call that alkylation. Okay, so far, what have we done? We now know how to go from, let me take this out of the way. Okay, so now we know how to go from this molecule here to this molecule. Now the next question you want to ask yourself is, how do you make this molecule? Keep in mind what you want to do, you want to come back to here. Okay? Okay, let us see. How do you make that molecule? Okay, then you say, oh, to make that molecule, all I need to do is this here. I take this here. So somebody's asking, lithium in ammonia do the same thing as, yes, the lithium in ammonia will do the same thing as sodium in ammonia, yes. Okay, so now you say, okay, I take the acetylide, I react with sodium amide, this here. This molecule is what we call sodium amide. That will deprotonate, take a proton away from the terminal alkyne to form this here. Okay? Okay, so now we know how to form this here. Then the next question you want to ask yourself is, how do you form this? How do you form this? Keeping in mind that you want to come back to, let me narrow this down so we can see. Okay? Okay? Keeping in mind that you want to come back to this here. To this right here. Okay? So how do you form this? Okay, then you say, okay, to form that, I'm sorry, this should be going forward. Let me erase this. This arrow should be going forward. Keep in mind what we are doing here, we are going backward one step at a time. Okay? Okay? Now, so now we go by one step at a time. Now the question, keep in mind you are keeping an eye on the starting material. How do you form this? Okay? Which is an alkyne. How do you form that? Okay, then you say, oh, to form an alkyne, I will form an alkyne this way. I take this here. Okay, we have two carbons there, right? We have bromine and bromine, a dibromo compound. Okay, if you take a dibromo compound and you take either sodium amide, let me use a different color pen. If I take sodium amide, or potassium hydroxide. Those two reagents, they will convert a dibromo compound, this here, to the terminal alkyne. Okay? So now, we're getting close to our starting material. Then the next question is, how do you make this compound? The dibromo compound. Okay, then you say, oh, can anybody answer that question for us? How do you make the dibromo compound, keeping in mind your starting material? Anybody has an idea now? We are almost there. How do you make this dibromo compound? Okay, add bromine to the starting material. Excellent, excellent. So now what do we have? We now simply now take this. This is our starting material. Add bromine to this in the presence of dichloromethane, and you get your dibromo compound. So therefore, what do we have here? Let me take all of this out of the way. So therefore, okay, so let me take all of this out. So now we'll see, become very clear. So what I've given you here is what we call a synthetic scheme. And what have we done? We started with this compound. We reacted that with bromine in the presence of this solvent here, dichloromethane. We got the dibromo compound. Then we got the dibromo compound. We reacted with sodium amide or potassium hydroxide, and then that gives us the terminal alkyne, which is this here. Terminal alkyne. Okay, so once you get the terminal alkyne, then you deprotonate the terminal alkyne, deprotonate, in other words, remove the hydrogen from it. With sodium amide, you now get the sodium acetylide. Yes, somebody say, can you use DMSO for the solvent? In this case, right? Yes, you could use DMSO or tetrachloromethane. You could do that. Any of those non-polar solvent or non-nucleophilic solvent you could use. Okay, for in this part instead of the methylene chloride. Okay. So now we react the sodium acetylide with methyl bromide to get this compound here. You get the alkyne, and finally you react the alkyne with lithium in ammonia or sodium in ammonia to get your final product. But the lesson here is, unless you know your reagent, you cannot do this problem. Okay? Most of you who have come to my office, I tell you, knowing your reagent is the ABC of organic chemistry. Because what most organic chemists do, when you make new drugs, when you make new pharmaceutical drugs, you need to be able to put together a synthetic design. For you to do that, you need to know those individual reagents. Okay, that is the only way you can do that. Okay, now if you follow this, give me a happy face. If you follow what we've just done on question number 5, give me a happy face. Okay. Okay, by the way, the video of this presentation will be made available to you by tomorrow. So I will email you to let you know where you can get the video. Okay, before we leave, oh my God, the time is about 8:20. Let us see if we can do question number 6. This is also a synthetic problem, and then after that we call it a day. Okay, let us see here. Question number 6. Let me see. Laura, can you go ahead and read question number 6 for us?
Outline a reaction to show how you would synthesize 2-dodecanoate starting from acetylene. Include all reagents at each step and show structure of all intermediates leading to your product.
Okay, very good, and thank you very much. Okay, yeah, before we go to this question, somebody say, what if I don't have your email? If I don't have your email, go ahead and email me tonight. Email me tonight and let me know that once you email me, and then I have your email. My email is f.ayorinde@howard.edu. Okay, so go ahead and email me, and then I will include your name in my email list. Okay, now let us attack this problem. Okay, so now they want us to make this compound here, this very big molecule here, starting from acetylene. Okay, from a very small molecule. Okay, we all know what acetylene is. This is acetylene. Okay, very small molecule. So they want us to make 2-dodecanone from acetylene. Okay. Now what you want to do, just like we did before in the previous question, you want to take a look, do an analysis, and take a look of what exactly do you have here. What is the transformation that is required here? Okay, so let us do that. I will say, okay, let me take this out of here. Okay, let me number this here, just for the sake of our analysis. Okay, let us call this carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 carbons here. We have 12 carbons here. Now, since they want us to start from acetylene, I am going to make an assumption right away that this functional group right here will be coming from acetylene. You have to make that some assumption that, okay, this functional group must be coming from acetylene. Then you then want to ask yourself, how do you get a ketone, a methyl ketone, from acetylene? How do you get a methyl ketone from acetylene? How do you get methyl ketone from acetylene? Anybody answer that question for us? Just when I say acetylene, it could be acetylene attached to some alkyl group. Okay, let us say we have R here somewhere. Does anybody have an answer to that? How would you get a methyl ketone from a terminal, let us say a terminal alkyne? Anybody? If you add on the cane to acet, and then there with, no, not exactly, no. Okay, okay, keep trying, keep trying. Not from alcohol, no. No. Oh, okay, you're almost there. The opposite of hydroboration. Somebody say hydroboration. The other one, the other one. Keep trying. Not hydroboration. There is another one that will do it. There are two reagents. Okay. Oxymercuration. Excellent, excellent, excellent. That is correct. Okay. Once you know that, okay, so let us see here. Let me take this out of here. So we know that if we take a terminal alkyne and we take this reagent here, mercury sulfate in sulfuric acid, or sometimes you just write in hydronium ion, what that gives you is this here. It gives you a methyl ketone. In other words, this carbon here, the terminal carbon, no, let me change the color. The terminal carbon, this carbon here, becomes a methyl carbon, and this carbon here becomes the carbonyl carbon. Okay? So that is what that gives you. So therefore, this reagent, you need to know this reagent. That is what that reagent will do with a carbon-carbon triple bond, a terminal carbon-carbon triple bond, terminal. Okay? Okay, having given you that information, let us now go back and see how we can solve this problem. Okay, let's see how we can solve the problem. Okay, we're starting with acetylene. Acetylene only has 2 carbon atoms. 2-dodecanone has 12 carbon atoms. And we already agreed that this part of the molecule must be coming from the acetylene. Okay? So if that is the case, therefore, what do we need to do? Somehow we need to join this carbon to this carbon. Join this carbon here to this carbon. So we have to form a new carbon-carbon bond. And how do we do that? To do that, we take acetylene. You guys should know that by now. Sorry. Take acetylene, react with sodium amide, and what does that give us? We form the acetylide. We form the acetylide, sodium acetylide, and then once we do that, see, let me just. Okay, now once we do that, we form the sodium acetylide. Does anybody now know what we need to do to form a new carbon-carbon bond? Anybody has an idea? Okay, we form this acetylide here. Okay, make acetylene. Okay, very good. Then what do we need to do now? We need to form a new carbon-carbon bond. This should be fairly simple. Okay, okay, alkyl. We use an alkyl bromide. Okay. What kind of alkyl bromide are we going to use? Keep in mind we have 12 carbon in the molecule. We have 2 of them in the acetylene already. So therefore, how many more carbons do we need? How many more? I have to leave. Yeah, okay. How many more carbon do we need? 10 more carbon. Okay, so therefore we take this. Okay, so we take, let's see if we can get 10 carbon here somewhere. Okay, 1, 2, 3, 4. Oh, sorry about that. Let me go back to that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the bromine is here. Okay? So if we do that, we get the acetylide attacking so the acetylide here will attack the bromide, and so therefore we get this product. Okay, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now the acetylide is now here. Okay, so now we form this. So once we now form this, Now what do you think will be the next step at this point? We now form this compound here, the terminal alkyne. What will be the next step? Anybody? Okay, oxymercuration. Very good. Excellent. Okay, let me narrow this down here so that we could see this better. Okay, so once we do this, now we take we take this here, take all this out of here. Take this out. Let me take all this out. Now we could now do this. Just simply take this here. Now react with mercury sulfate. Okay, in the presence of either sulfuric acid or hydronium ion. And so therefore this is a very simple synthetic process. Very, very simple synthetic process. So what have we done here? We started with acetylene. We formed the sodium acetylide, and then we react the sodium acetylide with bromodecane, which is this here, bromodecane, and that will give us the terminal alkyne, which is here, and then we react the terminal alkyne with mercury sulfate in the presence of dilute acid, and we get our final product, which is this here. Okay? So, but folks, you cannot do any synthetic problem unless you know all of those reagents. So I beg you, take your time, memorize all of those reagents, make up a list of reagents, because if you don't, you cannot do anything in organic chemistry. So at this point, unless there is some question that you guys have, we have come to the end of today's presentation. I want to thank all of you for being here. But before I do that, let me recognize those of you who are still here. I see here, Bukola is here, Chelsea is here, Dominic is here, Jared is here, Joy, Kessler, Laura, Nicole, Ore is here. Okay, let's see. Tamara, Hugo is here, and Valencia. All of you enjoy the rest of your evening, and I thank you for your time today. And for those of you who have a few more questions to ask me, when we end the session, I will stay around for another 5 minutes. Okay, I will stay around for another 5 minutes. But in the meantime, I'm going to turn off the recording so the session will be officially over.